Morning AP Chem. Today we're going to go over Unit 7.4 through 7.6, which involves calculating the equilibrium constant, understanding what the magnitude, the number of the equilibrium constant actually tells us about the equation and the reaction, and properties of the equilibrium constant. Okay, so we're going to jump right in with some examples. Calculating case C. We have a system that establishes equilibrium at 500 degrees Celsius in accordance with the chemical equation below. So N2 gas plus 3H2 gas yielding 2 NH3 gas. The following concentrations were measured. Calculate the value of equilibrium constant case C. So all three of these concentrations, which again are molar concentrations, moles per liter, these are concentrations that are measured at equilibrium. So our first step is to actually set up what our Kc equation actually looks like, okay? So remember, we're going to take the concentration of our product to its stoichiometric coefficient power, divided by the concentration of our reactants to their stoichiometric powers. Since all of these are gases, all of them will be included in the final concentration, or the final equation, but that's not necessarily always true if we have solids or liquids present. Okay, so our equation should look like this. From here, it's just simply plug and chug. So we're going to plug in the concentration of NH3, the concentration of N2, and the concentration of H2. And remember, we have to square the concentration of NH3 and cube, there we go, the concentration of H2. Equilibrium constants do not have units, so all units end up canceling out. So that's really simple and easy. So if we plug and chug here, you should end up with a Kc value of 6.49 times 10 to the negative 2. And again, there is no unit associated with that. So here's another example. This time it establishes equilibrium at 485 Celsius in accordance with the chemical equation below, and we record the partial pressures of the reactants and products. Calculate the value of the equilibrium constant Kp. Okay, so this is very similar as the process before. Remember, we're using rounded brackets for our expression. All of these are gases, so they will again all be included. So our equation should look like the pressure of hydroiodic acid squared divided by the pressure of hydrogen gas and the pressure of iodine gas. If we plug in those values that are given, we have 0.28 squared divided by 0.035 times 0.045. Plug that into your calculator, and you should find the Kp value of 49.8. So what do these values actually mean? K equilibrium actually tells us a lot about how this reaction lies. So if we get a value that is basically less than 1, that means that our numerator is significantly less than the denominator. In the numerator, we have our products. In the denominator, we have our reactants. So this tells us that the products are a lot less than the reactants, whether it's pressure or concentration. In this case, it's the pressure of the products is less than the pressure of the reactants. So when K equilibrium is less than 1, that tells us that the reaction favors the left side of the equation. It favors our reactants. If it's less than 0.01, then that tells us it strongly favors the left, strongly favors the reactants. So remember, partial pressures are proportional to the number of moles. So the greater the partial pressure, the more moles that we do have. So in this case, we have mostly reactants at equilibrium. If we have a KEQ value that is greater than 10, that tells us that the numerator outweighs the denominator. We have a larger numerator than denominator. Products are located in the numerator, so that tells us that our concentration or our partial pressures are favored to the right side of the reactants. So it favors the products. If we have it KEQ that is greater than 10, the equilibrium strongly favors the right side, so it means that at equilibrium we have mostly products. So again, if we have a KEQ value of either Kc or Kp, sorry, I use those kind of interchangeably, but KEQ kind of includes KC and KP. I don't know if I ever clearly expressed that, but the KC and KP are both types of KEQ, if that kind of makes sense. But anyhow, so again, if it is less than 1, we have mostly reactants at equilibrium. If it's more than 1, especially if it's greater than 10, we have mostly products. If it was equal to 1, that would mean that we have equal amounts of products and reactants. This slide kind of sums that up. So KEQ greater than 1, we have mostly products. Equilibrium lies far to the right. KEQ less than 1, we have mostly reactants. Equilibrium lies far to the left. And if KEQ is about 1, we have pretty much equal amounts of each. So equilibrium lies in the middle. So here, example 3, we are considering what the value of KEQ means. So the particulate representation below describes the following reaction when it has reached equilibrium. Is the value of equilibrium constant greater than, less than, or approximately equal to 1? So here we have the reaction AB yields A plus B and vice versa. It is a reversal reaction, and we know that because of the double arrows. So here, the particulate representations, AB is going to be the blue and green molecule. I'm going to call A green and B blue. So here I'm going to count how many of each we have. So AB molecules, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, so I have 16 AB. I think I said A would be green. That tells me I have 1, 2 green and 1, 2 B, which are blue. Okay, so I have 16, 2, and 2. This tells me that I have much more reactants. I have 16 versus 2 of each. So that tells me that the equilibrium lies to the left, favoring reactants by the way that this is currently expressed. So my KEQ value, KC in this case, should be less than 1. So the concentration of reactants is much higher than the concentration of products. We can manipulate K and Q values. So again, K describes equilibrium. Q can be pretty much any point in the reaction, including equilibrium. So there are 3 ways that we can kind of manipulate these values. Those are the coefficient rule, the reciprocal rule, and multiple equilibria rule. So first we'll talk about the coefficient rule. So when coefficients are changed by a factor of n, KEQ, or Q, would be raised to the power of n. So in this example here, we have equation 1 and equation 2. Comparing the two to go from 1 to 2, it looks as though we have everything or multiply by 1/2. So A's coefficient goes to 1, B's coefficient goes to 1/2, and D's coefficient goes to 3. So to find the K value for the second equation, if we had the K value of the first equation, all that we would have to do is raise this entire expression to the 1/2, and that's what they do right here. So this system doesn't really change, or this process doesn't really change the equilibrium. And the best way to think about this is like you have a reaction taking place that we'll call the system. So the physical experiment doesn't really know what balanced chemical equation you're using, you know? So whether you're using this equation or this equation, the reaction doesn't know. It's just going to proceed using the stoichiometric coefficients that it proceeds by. So it's kind of following its own rules. The reaction doesn't know which equation you're using, it's just reacting as it does. So at equilibrium, the concentrations are going to be the same, whether you did this experiment focusing on the first or the second equation. Again, the system doesn't care what you did. It's going to do its own thing. And at equilibrium, those concentrations are going to be the same no matter what. Okay. So the stoichiometric ratios are still the same between both equations. Okay. we still have twice as much A as we do B in both equations. And we still have 6 times more D than B in both equations. The concentrations of products and reactants would not change if you double the stoichiometric coefficients or divide them in half. The system, again, doesn't care what you're doing, what equation you're using, it's doing its own thing. So if you start with one balanced chemical equation, you have to do all the math using that same balanced chemical equation. If one person works out the problem using this Kc expression and another person uses this Kc expression, they're both going to get the same values for final concentrations at equilibrium, even though they're different expressions. Okay. For the reciprocal rule, so if we switch the reaction, so put products in the reactant side, the new KEQ value is going to be the inverse of the old KEQ value, which makes sense because remember, for K values, we have the concentration or pressure of reactants on top divided by the, did I say reactants? The concentration or pressure of products on top divided by the concentration or pressures of reactants on bottom. If we flip that equation, those two things are going to flip. So it makes sense that we use the inverse, okay? So here we have the inverse here, and they're defining this equation as 3. So we have d to the 6 over a squared times b. The inverse of that equation, that Kc expression, will be described as a squared times b divided by d to the 6. Okay, so it's just the inverse. You just flip the expression. Okay, and finally we have the multiple equilibria rule. So when 2 or more reactants are combined, the new K equilibrium is the product of the K equilibrium values from the individual reactions. So if we find the KEQ expressions for reaction 1 and 4, multiply them, we get the KEQ, Kc in this case, expression for the overall reaction. Here we have A kind of working as a catalyst, so they end up kind of canceling out in those equations. But this here is the first Kc expression for 1. So we have d to the 6 divided by a squared times concentration of B. And then we have to multiply it by equation 4's Kc value, which is going to be F times concentration of A squared divided by concentration of E cubed times the concentration of B. If we multiply those together, we get the overall Kc value for the final equation. So you can see how that matches up with the final equation. Okay. So that is it for our section 7.4 through 7.6 notes. I do have a worksheet uploaded for us to work on. Let me know if you have any questions.